Hello, welcome to Unit 4, Lesson 4. This is graphing polynomials, and this video has been updated for the 24-25 school year because of the timing of the lessons and how the last two sections were covered and when they were covered. So if you are watching it for this year, 24-25, awesome. This is going to give you a great review and coverage of the new material. If you are watching it for a different year, I guess just follow whatever directions I gave you for watching the video and taking notes, or what you were responsible for what's in it. So I wanted to begin with a summary of the last class. So the last class, we did an investigation activity where you were given a bunch of sums and differences of cubes and then asked to pair them up with the factors that go with them. And we did a little bit of a lesson on what cubes are, what perfect cubes are, just reviewing that vocabulary of sum and difference. And so you had 10 of these. These are not necessarily the same 10 that you did, but they're like other examples, and some of them might match up. So the first thing I want to reflect on, and what we'll talk about in class, is how did you match them up? Now, if you weren't present in the last class and you're doing this as kind of a refresher or to make up that material, pause the video and think for a moment about how you could match up the expression on the left with the expression on the right. Now, I think what most of the groups did was they did multiplication. So I'll take a look at this one. So what most groups did was they divided up the work, and this is where working in a group can be a huge advantage to going solo, and did the multiplication. So x times x squared is x cubed. This gives us 3x squared. This is 9x. This is negative 3x squared, this is negative 9x, and this is negative 27. And then to get the product, we need to find the total area, which means we need to add all those little areas up. And what we notice is that our like terms actually cancel each other out. So we have negative 3x squared and positive 3x squared and negative 9x and positive 9x, and they end up dropping out, leaving us with x cubed minus 27. And so you would go through your stack of expressions, and you would find the x cubed minus 27, and you would like match those up. And so the best way to do this was probably to divide and conquer. So if you were in a group of 2, 3, 4 people working together, you would each take 2 or 3 of the expressions and multiply them out, and you would get them all matched up. And that would review the multiplication process. It would review several different concepts. So now you could do this other ways though, because x cubed minus 27 and x minus 3 times x squared plus 3x plus 9 are just two different ways of writing the same thing. Another option you would have would be to graph it and then see which of the graphs matched up. Now, I think there were some people that did that as a check, especially starting out, so they weren't sure if they were doing it right. And so they opted to graph like the first couple of them just to make sure that the strategy that they had chosen worked, which I think is great. I think the graphing takes quite a bit longer in a problem like this, because if you don't know which ones are going to match up, you could go through a lot of typing into Desmos before you could match them up. So at the end of the day, most of the groups got most of them matched up. And you were asked to describe your method. So hopefully you would use correct math terminology, like we multiplied the factors together. Now, the next task was the one that a lot of people struggled with, and that was looking for the patterns. And I gave you some hints about like what to look for. So to look for patterns in the operators. So the operators are the pluses and minuses. And one of the things I had hoped that you would notice is that the original operator always matched the first operator in the first factor. So if I go down here, you'll notice that like a minus gives you a minus in the first parenthesis, a plus gives you a plus in the first parenthesis, so that those operators always matched up. And then going to the next operator, several groups noticed that it was opposite. So I got like they switched or they flipped. The math word we're looking for there is opposite. So if the first one was a minus, the second one was a plus. If the first one was a plus, the second was a minus. Okay. And so you'll notice that it always flips. And that third operator down here was always a plus sign in all of the problems. And so that is one of the patterns that I was hoping that groups would notice, that you have the same operator as the original, then the next operator was flipped, and then the last one was always positive. So that's one of the patterns that you might see. Now, there are also patterns in the numbers, however. And so I tried to prompt a couple people to kind of look at this. Everywhere you see a 27, a 3 would pop up, okay, in the corresponding spot in that first parenthesis. So 27 always changed to a 3. A 125 changed to a 5. Let's look and see what else we got there. We have 64 comes up in a couple places, and the 64 is always a 4. And we also have an 8 there. An 8 in a couple places always morphs into a 2. Now, as you're looking at that pattern, it should ring a bell from the lesson part where we talked about cubes, perfect cube numbers, and what number like gives you a perfect cube. And so looking at the 27 here, 3 to the third power is 27. And so you would be looking at what to the third power gives me this. Right here in the second line, 2 to the third power is the 8, and 5 to the third power is the 125. Now, it also works for the ones. Okay, we have a couple of ones there, and 1 to the third power would give you 1. Okay, that looks terribly written there. 4 to the third power would give you that's a 4, would give you the 64, and so forth. And so looking at the numbers in the original problem, when you were looking at the factors, you were looking at the numbers that would give you those perfect cubes if you were to cube those numbers. So that's a really, really important pattern to notice as well. And I understand that it might be difficult to describe those patterns, so finding the words to describe them, but that is an important skill, is being able to communicate what you're seeing. And so that is something that's worth looking closer at. And then within these, I want you to notice that the first term is always squared to get the first term in the larger parentheses. So x, and it becomes x squared. 2x becomes 4x squared. So you're squaring the 2 and squaring the x. 4x becomes 16x squared. Here we have another x. 3x becomes 9x squared, because 3 squared is 9 and x squared is x squared. And then the same thing happens on the other end. If you square 3, you get 9. If you square 5, you get 25. If you square a 1, you get a 1. If you square a 4, you get a 16. If you square a 2, you get a 10. Okay, or 2, you get a 4. I don't even know why I said 10. That's weird that came out of my mouth. Okay, so there's that pattern there. And then there's another pattern you could see. And that's where this middle term comes from. And it comes from multiplying these two things here. So 3x times 2 gives you 6x. X times 4 gives you 4x. 4x times 1 gives you 4x. 2x times 5 gives you 10x. Sorry, my handwriting is really bad there. And then x times 3 gives you 3x. And so that was another pattern you could see. So the way that this was graded was, I think there were 4 or 5 different patterns you could see. If you could explain like 2 or 3 of the 4 or 5 that were there, and you could explain them in a way that I think you were seeing the right thing, then you would have gotten full credit. You didn't have to see everything, and you didn't have to explain it perfectly to get full credit. If you only wrote down one thing, then that's not enough. There were a lot more patterns to see, and you needed to take some time to look more closely at those patterns. that were there and like try to find more rather than rushing on in the activity to try to answer all the questions and just get it done. Because those patterns lead us to the next thing, which is what we call the SOAP sandwich. And this is just a way to remember. Now I'm questioning my spelling of sandwich. Sorry about that. But it's a way to remember the pattern. So the SOAP part of the SOAP sandwich stands for this. It stands for same, opposite, always, positive. And that is a way to remember the operators. So if I look at, I'll do that first example down here. So the 125 x to the third, you have like the small parenthesis and then you have the big parenthesis, and the operators are going to be the same, the opposite, and always positive. And same with the next one down here, same, opposite, always positive. And so that is one way just to remember what the operators are, and it's a great way to eliminate incorrect answer choices when you are doing multiple choice. Now the sandwich part is square it, smash it together. So if you picture like a sandwich, you got like 2 slices of bread, okay, and bread is typically square, okay, so bread, square, and then you have your filling, like we'll call it like a PBJ, and you're just gonna like smash it together. And so that tells you what goes in between those operators. So so the first parenthesis, you just use the cube root. So what to the third power gives me 125? Well, that would be 5. And what to the third power gives me x cubed? That's x. What to the third power gives me 1? That's 1. And then for the sandwich, we're going to take that first parenthesis and we're going to square it, smash it together. So 5x times 5x is 25x squared. 1 times 1 is 1, and then I get the filling by taking the 5x times the 1, that's the smash it together, the PBJ. 5x times 1 is 5x. Doing the next one down, what to the third power gives me 64? Well, that would be 4. What to the third power gives me x cubed? That would be x. And what to the third power gives me 8? That would be a 2. And then we're going to square it, smash it together. So 4x squared is 16x squared. That was like here, and 4x all squared gives you 16x squared. Okay. 2 squared gives me 4, and then 4x times 2, that's the smash it together, is 8x. Now, this one is actually not fully factored because you'll notice I have all those even numbers in there. And so if you notice that, it means that there was probably a GCF at the beginning of it. And we've done this before in previous lessons, so I really don't want to belabor the point. But if you do notice that that's happened, you can do 2 things. You can either go back and start the problem again and get the common factor out, which the common factor there is 8. Okay, and then you're left with that, and then you can factor it here. So same, opposite, always positive. What to the third power gives me 8? That's 2. What to the third power gives me x cubed? That's x. What to the third power gives me 1 is 1. And then I would square it, smash it together. Or you can actually keep the factoring that you've got and look for the GCF inside of it. And so you could look at this and you could factor a 2 out of the first parenthesis, giving you 2x minus 1. And then you could get a 4 out of the second parenthesis, leaving you with that. And then 2 times 4 would give you the 8. So either one of those would work. So that is the mnemonic device. Hopefully that makes sense. And hopefully if you were absent last class, you've already seen this, that you looked up what we were doing. You watched the videos that you were supposed to watch to make up that material because. All right, on to the next thing. So the next thing was factoring by grouping. And when you watch the video for this, the video contrasted the traditional layout with the area model. Factoring by grouping is very trivial with the area model. It does not require a lot, but I did want to show you the traditional layout, which I have over here. Okay. So they're really the same method. They're just laid out on the page differently. And my experience with students is that like when you're grouping and you're chunking it like that, and you're looking for these individual GCFs, okay, and then you're dealing with a GCF that is actually a binomial, that is very difficult for students to see, that you just aren't used to seeing a common factor that is a binomial. And what makes me a little suspicious when I see a lot of students doing this, particularly with earlier problems, is that I know that most of the apps that are out there, apps and websites, will factor this way. And it's a perfectly valid way to factor. There's nothing wrong with it. It's just when I do teach it, like students struggle with it. So I tend not to think that, oh, yeah, sure, that's obviously the best way for you to do it, unless copying it off of the internet is the best way to do it. Now, for the area model, it's actually really, really straightforward. So for the area model, you would take the x to the third would go in the upper left, and the negative 15 would go in the lower right. And then you can actually place the negative 5x squared or the 3x wherever you want. I'll go ahead and put them here. Okay, and 3x. And then you just GCF factor. So it really is the same method. So if you look at x to the third minus 5x squared, what is the greatest common factor? Well, that would be an x squared, which means to get the x cubed, it would be x squared times x, which means that this must be a 3, and this must be a negative 5. And so your base times your height is x minus 5 and x squared minus 3, or plus 3, sorry about that. And that it's really a much better way of laying the factors out on the page. So that's really all there is to that. Now, the only other thing that was covered in on your classwork, you needed to copy down a problem as it was done in the video, and people did not quite finish copying it down. So let's just make sure that we are all good on this. So we have 2x to the third, we have x squared, we have negative 128x, and we have negative 64. And so I will GCF factor going this way. So the greatest common factor between 2x to the third and x squared is x squared, which means that this must be 2x, that must be a 1, and this must be a negative 64. And so your base is 2x plus 1, and your height is x squared minus 64, except that that is not finished being factored, because this time we actually have the difference of squares, which was on our Unit 3 test, and difference of squares factors into what are called conjugates. And so we would have a plus b and a minus b, so it would be x plus 8 and x minus 8, and you would get it completely factored that way. So there was a little bit of an issue with the problem that you were supposed to copy down. You do need to like copy the entire thing down, and you need to watch the videos with the sound up. And I know that I am not the most interesting person to listen to, nor is math the most enthralling thing to watch. But if you're just watching it, then you could very easily be missing something that I am saying. So just be mindful of that. All right, so that was our reteach on the material from last class. Now, graphing polynomials, we're going to do this the fastest way we can, because this is typically done using technology. And the first slide on this is like the ancient way, pre-technology versus the current way with technology. It's really changed why we graph polynomials and what we're looking for in the graphing of those polynomials. So the ancient way, we would find key points using substitution and factoring. It would be a very, very long process. So we would find the x-intercepts, we would find the y-intercepts. We would have to do a lot of factoring, which is part of why factoring would be such an important skill, because we would need it in order to be able to find the key points. Then we'd use theorems to test for positive and negative intervals. So we would find all these key points, and then we need to find out where is it above the x-axis, where is it below the x-axis, and does it change like every time you cross, or does it bounce off of, things like that. And then you would the whole thing would result in this rough sketch. Okay, and so you do all this work to come up with a rough sketch. Now the current way is, it's almost backwards. So the current way, you would use a graphing utility to generate an accurate graph. So it's almost like we're starting where the other way ended. The difference is that the other way would require you to engage all kinds of knowledge about increasing, decreasing, positive, negative, and behavior, things like that, just to get the sketch. And now we would just more get the sketch and then identify those things. So it's much, much, much easier provided you know the vocabulary. So you identify the key features off of the graph as applicable to whatever context the larger problem is. And so where something is increasing or decreasing or positive or negative depends on the bigger problem. If you think about a problem that, say, involves like money, okay, and you've got some kind of like thing with money, above the x-axis would mean that you have money, below the x-axis would mean that you are in debt. Positive slope or increasing would mean that you're gaining money. Negative slope would mean that you're losing money, and so that would be decreasing. And so the broader context of the problem would tell you what those different intervals mean and why they are important. Okay, so what do you need to be able to identify? What are the things that, for those of you moving on, you're going to go to pre-cal next year and you're going to sit in that class and people are going to talk about, they're going to talk about more than just this, but like, what do you need to come into that class already knowing so that you are not drowning? Well, you need to know the number of roots, zeros, x-intercepts. So that is new material that we'll cover today in this lesson. Okay, how do you determine the number of roots? It's super easy. How many of the roots are real versus how many are complex? That's also new material, and it is not remotely difficult. You just need to remember what I'm telling you. We'll go through, we'll justify it with some examples, and then you need to practice it enough so that you don't forget it. The y-intercept, that is review material. That's where the graph crosses the y-axis. It's also where your x value is 0, so it's usually fairly simple to find. So you can plug in x is equal to 0 into the function, and it'll dump out the y-intercept fairly quickly. I lost my little mouse. There. Okay. Intervals of increasing and decreasing, that means whether it's heading up or heading down. And I do have a slide coming up where we'll define all those things again if you need it. Intervals where it's positive or negative, that's above or below the x-axis. That's also review material. End behavior, whether or not it goes up or down at the ends, and you would just simply say what end it is. It is the right end, and then it goes up or it goes down at the right end, and then you'd say like the left end, and then whether it goes up or down. All right, so let's look at how many roots, zeros, or x-intercepts. So those are all synonymous words, okay? So roots, zeros, and x-intercepts are all synonymous. The number of roots is equal to what's called the degree of the polynomial. Okay, and so it is literally that simple. Now, of course, we have the vocab issue where I say the number of roots is equal to the degree of the polynomial, and you're like, okay, that's great. What is the degree? Well, the degree of the polynomial is simply whatever the highest exponent is. So that covers that first thing, like how many roots does a polynomial have? You go and you find the highest exponent. That's how many roots your polynomial has. So for example, f of x equals 2 to the third minus 4x plus 5. You see that the highest exponent is a 3. That has 3 roots. Okay, that's simple. The only way you get this wrong is if you just do not study or prepare. Like this is not difficult. So take a look at that one and tell me how many roots that polynomial has. And hopefully you saw that the highest exponent was a 5, and so you would answer 5. Now notice the 5 was not on the left. That's because that polynomial was not in standard form. Usually they are in standard form, but they don't have to be. It doesn't change how you decide how many roots you have. And we could do a lot of examples with this. The problem is that some of the roots are like you're going to see and some of them you don't. And so it's a little bit harder to curate the examples so you can see it. Now, what about something called complex roots? Okay, so this is review as well. This is a reteach. So a complex number has a real part and an imaginary part. Imaginary. There we go. And it takes the form a plus bi. And so like an example would be 3 minus 5i. That's your complex number. If the root is real, okay, so if the root is real, we'll see it on the graph as an x-intercept. Okay, if it's a real number, we will see it on the graph. But if the root is complex, we will not see it on the graph. Okay, and this is something that you probably want to write down. So if the root is complex, we will not actually see it on the graph. So total number of roots is equal to whatever the highest exponent is. That's called the degree. So you might have 2, 3, 4, 5, whatever you have. Any roots that are real, when you graph it, you will see them on the x-axis. You'll see them. And then whatever is left over must be a complex root. So you know how many there are total. You can see how many of them are real. And so the rest would be complex. So here's an illustration. Okay, we have y equals x squared minus 2x plus minus 5, and recall that the x-intercept is where y is equal to 0. Okay, and so we'll do like a little. All right, so x-intercept, what's the y value of that point? The y value of that point would have to be 0. So if we go ahead and solve this equation, we'd have 0, because we're plugging in y is equal to 0, is equal to x squared minus 2x minus 15. And so you might do a quick area model here to get that factored. We need 2 factors of 15 that add up to -2, and they would be -5 and +3. And so we get that factored. So we have 0 is equal to the base, which is x minus 5, times the height, which is x plus 3. And then we use the zero product property, and we know that if we have two things multiplied together whose product is 0, then the one of those factors has to be 0, so it could be the x minus 5 or the x plus 3. Add 5 to both sides, and we get x is equal to 5. Subtract 3, and we get x is equal to -3. Okay. Now, if I go and look at the graph for that, you will notice that we have x is equal to -3 and x is equal to 5. No, just notice the whole thing though, that you've got x is equal to -3 when the y value is equal to 0, and you've got x is equal to 5 when the y value is equal to 0, which is exactly what we did. We plugged in y is equal to 0 and then solved the equation and got the -3 and the 5 from the algebra equation part, but it also corresponds with the graph because this is all just, it's all just ways of seeing the same thing. So, so the roots there are -3 and 5. There are 2 of them, and we can see both of them. They are both real numbers. If I went through that really fast and you need to rewind this to like kind of watch that again and catch up with the writing, please do. I know this lesson video is long because it covers the recap of last class as well. All right, so here's another one. So the x-intercept is, again, where y is equal to 0. So if I plug it in here, I have x squared plus 9. Now, we've actually done this problem. This problem was done in an earlier lesson. So we subtract 9 from both sides. We have to do the square root method on this. And we're looking for a number that when squared gives us -9, which is not a real number. If you have a negative under a square root, you know that that generates an I. And so we get x is equal to plus or minus 3i. Now, again, I went through that fast because we've actually done that same problem in class before when we were going over different ways of solving quadratic equations. Now, if I look at the graph for this, you will notice that there are no x-intercepts. Okay, now there are two roots. The two roots are positive 3i and negative 3i, but they are complex roots or imaginary roots, and so they don't show up on the graph. All right, so that's the illustration there that illustrates a couple of things. One, that we know that there are two roots, so whatever the highest exponent is, that's how many roots you have. If they are real, you will see them. If they are imaginary, you will not see them. Okay, it doesn't mean that there aren't roots, it just means that they don't show up on the graph. So where do we go for there? Can we have a combination? Yes, absolutely. So it's not like all the roots are real or all the roots are complex. If you look at this one, we know that there are three roots. Why do I know there are three roots? Because the exponent is 3. The highest exponent is 3. Degree is 3. Now, when I look at the graph, though, so this polynomial has 3 roots total. One of them I can see. So one of those roots is real, which means that the other two roots must be complex because they have to add up to 3. So you have the total number, which is 3, and then you have however many you can see, which could be 1, 2, 3, 4, 5, whatever, however many you can see. And then however many are left over are the ones that are complex. You might not have any complex roots. You might have tons of complex roots. Just you can see the real ones and the other ones are complex, and they have to add up to the total number of roots. Now, key fact, complex roots always come in pairs, and that's because they get generated from the plus or minus b squared minus 4ac. Okay, they get generated out of that, and so you'll always have a plus or minus of the same thing, whatever that is. So you can never have an odd number of complex roots, ever, ever, ever. So if you're looking at a multiple choice question and it says like that the roots are x equals 3 and x equals 4i, you are not picking that, because if there's a 4i, there has to be a negative 4i to go with it. If there's a 2 plus 2i, there has to be a 2 minus 2i to go with it. Complex roots will always, always, always come in pairs. So never pick anything as a multiple choice that would show that there's only 1 or 3 or some kind of odd number. Okay, now the rest of the material for the entire lesson is review, and so I am aware that this video is getting very long. Kind of makes me dread how class is going to go. Actually, I'm thinking we're not going to finish the whole lesson in one class period, so you know what, just check Teams or whatever platform I'm using in any given year. So this is all review. You do not have to write this down unless you don't remember it. So x-intercepts, also called roots and zeros, are where the graph touches the x-axis. Okay, that's what they are. Y-intercept is where the graph crosses the y-axis. Okay. Increasing means it goes up from left to right. Decreasing means it goes down from left to right. Now, if I were taking notes on this, I might do something like that. Okay, that's not the greatest, but like do like an arrow. All right. So just your notes are for you to help you remember stuff. Positive means it is above the x-axis. Negative means it's below the x-axis. And end behavior is which way the graph points. Is it pointing up or down at the extreme left and right of the graph? So does it like go up forever, or does it go down forever? Like what does it do? Up or down forever? Okay, so here's an example, and I did clean this up because some of the questions did not work right. So how many zeros are there for this? Well, we would go and find the highest exponent, 3. That's how many zeros there are. And you'll notice that I do change up the vocabulary. I'll go zeros, roots, zeros, roots. I don't use the same word all the time. Both words are used, and both words are used a lot. Now, how many of those roots or zeros are real? Well, if you look at the x-intercepts, okay, I can see 3 of them. So if there are 3 total and 3 of them are real, then that means this one has no complex roots, and that's totally fine. If it did have complex roots, it would need to be an even number that we put there. So it would either have 2 or 4 or 6 or 8 or what are the real roots? Well, we can get those right off the graph. The real roots are x equals -2, x equals -3, and x equals 0.5. Do not overthink that. There they are. What is the y-intercept? 0, -6. There it is, right there. Okay, now increasing and decreasing cannot be seen on this graph with the information that we have, and I do want to talk about that for a second. Increasing and decreasing, just to review what they are, increasing is where it goes up from left to right, so it would be here, but it would also be that region there, and decreasing would be where it goes down. The problem is that we need to have the location of what are called the relative maxima and minima, and that information is not on the graph. It is very, very difficult to come up with polynomials that will have nice friendly points for all of your x-intercepts, and also the points where what are called the relative extrema, where they would like change direction. It's possible, like, but it's not something that like I could just stand there and like come up with something where all the points were going to come out nice. So this one has the intercepts coming up nicely, but not the other points. Okay, where is it positive? Well, positive is above the x-axis. So it is positive right here in between those 2 points, and then it is positive over there. And so if we were going to write that out, we would say it is positive between -3 and -2, and then it is positive again from 0.5 to infinity. That is my cat that you're hearing. I don't know if you can hear her. She wants me to play fetch with her, which is a thing. Yeah, there she goes. She just went across the room. All right. Where is it negative? Negative is below the x-axis, so it would be here, and then this chunk here also. And that would be from -infinity up to the -3, and then again between the -2 and the 0.5. All right, Hannah, go get it. Okay. I have no idea what the microphone's picking up for that. All right. So there we go. That's where it's negative. And then what is the end behavior? For your end behavior for this course, it is simply enough to say the left side of it is pointing down and the right side is pointing up. Okay, and you do want to indicate which side and then which direction it's pointing. So left, right, up, down. There's a much more precise mathy way of writing all of that we won't get into in this class. It's like using limit notation, and it's okay to save that for pre-cal. If anybody's really interested, I'm more than happy to explain it to you. All right, so here's a practice one. So pause the video and go through the answers to the questions. I'm going to send my cat across the room again. Okay, my cat really does play fetch. She's a 1-year-old, at least she's 1 year old at the time I'm recording this, and she's adorable. Okay, So how many zeros do we have here? Oh, you know what we don't have here is the original equation. So I'm gonna have to make an edit on that. This is a cubic. It is a cubic equation. So so there are 3. Yeah, I will change that when we're in class to make sure that I have that. So there are 3. So I'm so sorry if you said they were 1 and that 1 was real. You can give yourself like credit for that. Like you didn't misread it. That was on me for not catching that. I did edit like the previous problem and just kind of missed this one. I'll try to fix it when I do it in class. So we have 3 zeros. One of them is real, which means 2 of them have to be complex. And in sometimes like in an honors class, and I don't even know how much they do it there anymore, like you would have to go and find the complex roots. I am more interested that you know that there are 2 complex roots, not so much like can you find what they are. What are the real roots? Well, the real root is right there at -2, 0. So x is equal to -2. At the y-intercept is the 0.08. Where is it increasing? Ooh, I didn't quite mean to do that. Let's do. It's actually increasing everywhere. Now, right there, it's debatable. We can't really zoom in because of the way the graph is to see whether or not it levels off. And there's a point where it's actually horizontal. And I don't think that does make a difference in the definition of increasing. So we would say this is increasing everywhere, which means it's increasing all the way from -infinity to +infinity. For decreasing, it is not decreasing anywhere. Where is it positive? Well, it's positive beginning at x equals -2 and going to infinity. Where is it negative? Well, from -infinity up to the -2. And the end behaviors, the left is pointing down and the right is pointing up. So sorry about, again, just not having the actual function up there. But I'm not re-recording a 41-minute video. Not doing it. All right, so that's that. Again, if you're watching this to make up a class, do make sure you're checking in with me because this is a 42-minute video, and that means in class we're probably going to dive deeper into it than we do in the video. So like check with me to find out how much you have to do or what your next steps should be. All right, and that's it. I will see you in the next one.